Welcome back to Practical PyTorch. This is the last lesson of the playlist, and it is the payoff. Every piece you learned gets assembled into one working program on real images. This is the project, Fashion-MNIST Classifier. 14 lessons, one at a time. This one puts them together on real images. We build a classifier for Fashion-MNIST. 28 by 28 grayscale photos of clothing, 10 classes. The whole program is a pipeline of 6 pieces you already know. Data, a data loader, a model, a loss, an optimizer, and save. Each piece was its own lesson. Today they run end to end, and the model learns to tell a sneaker from a shirt. 6 pieces in order. First, the data. Fashion-MNIST loaded as a dataset. Second, the data loader. It serves shuffled batches of 64. Third, the model. A plain MLP 784 in, 256 hidden, 10 out. Fourth, the loss. Cross entropy on the raw logits. Fifth, the optimizer and its loop. Atom, run inside the training loop ring. And sixth, evaluate and save. Measure the test accuracy, then write the state dict. First, the data, and the data loader that feeds it. The first block of the pipeline is the data. TorchVision hands you the Fashion-MNIST dataset, so you download it in one line and get images with their labels. Each image is one grayscale channel, 28 by 28 pixels. That is the shape, 1 by 28 by 28, 10 clothing classes, all named, and the 60,000 training images split into 54,000 for training and 6,000 held out for validation, the split from the validation lesson. The 10,000 test images stay sealed until the final measurement. The connector shows the flow. The data feeds into the data loader. The data loader is the conveyor belt from the data lesson. It serves the dataset in batches of 64, reshuffled every epoch, and hands the training loop one images and labels batch at a time. One line sets it up. Data loader of the training set, batch size 64, shuffle true. The loop never touches the raw dataset. It just asks the data loader for the next batch. Shuffle true draws freshly mixed batches each epoch, so consecutive weight updates are not biased by a fixed ordering. Validation and test are served unshuffled, because shuffling is pointless when you are only measuring. Second, the model, the network that turns pixels into a guess. The next connector. Each batch flows from the data loader into the model. The model is a plain MLP, the NN, sequential from the model lesson. NN, flatten turns each 1 by 28 by 28 image into a 784 vector, then one hidden layer of 256 with array LU, then 10 output logits. Print the state dict shapes and you see 4 parameter tensors, 2 linear layers, each a weight and a bias. That is over 200,000 learnable numbers. This is a fully connected network. It throws away the fact that the pixels form a picture. That is exactly the weakness playlist 2 fixes with convolutions, but a plain MLP already gets surprisingly far. This is the same model in code. The whole network is one NN, sequential, a container that runs the layers in order. First, NN, flatten. It unrolls the little image into a flat row of 784 numbers. Then NN, linear of 784 to 256, followed by array LU. That is the hidden layer, and the array LU adds the nonlinearity. Then NN, linear of 256 to 10, 1 score per class, 10 raw logits. There is no softmax on the end. The cross-entropy loss handles that, and that is the very next block. Third, the loss, the optimizer, and the loop that ties them together. The connector carries the model's logits into the loss. 10 classes, so the loss is NN. Cross-entropy loss, the classification loss from the loss lesson. It measures the gap between the predicted class distribution and the true label. That gap shows as the red dashed marker in the block. One line makes it loss Fn equals Nn, cross-entropy loss. The one habit to keep: hand it the raw logits, do not add a softmax first. Cross-entropy loss combines log softmax and negative log likelihood in one stable step. A softmax you add yourself would be applied twice. This is the most common beginner mistake with this loss, and the model quietly trains worse when you get it wrong. The connector, the loss drives the optimizer. Adam from the optimizer lesson updates the weights, run inside the training loop ring over every batch for 5 epochs. Read down the epoch table. The loss falls every epoch and train accuracy climbs to 0.9, and the number that matters, validation accuracy, climbs too, up to 0.8893, tracking training closely. That small gap between them is a good sign. The model is generalizing, not just memorizing the training set. 5 passes gets us to about 88% here. First, the optimizer. Add them over the model's parameters with a learning rate of 1/1000th. Then the loop. We walk the train loader batch by batch. One full pass over the data is 1 epoch. This is the exact ring from the training loop lesson, now on real data. Forward, feed the batch through the model to get the logits. Loss, cross-entropy between those logits and the true labels. Zero grad, clear the old gradients from the last batch. Backward, fill in the new gradients. Step, update the weights. The order is fixed. Forward, loss, zero grad, backward, step. Forward, loss, backward, and step are locked by the data. Each needs the result of the one before. Zero grad is the one you place yourself. It must clear the last batch's gradients before backward writes the new ones. Fourth, measure the model honestly and save it. Training gun. Measure once on the 10,000 test images the model has never seen. This is the honest score. The curve shows both lines climbing together, train accuracy and validation accuracy, staying close the whole way. The final test accuracy is 0.878, about 88% correct on 10,000 images the model never trained on. Train and validation tracked each other, so the test score lands right where validation predicted. That closeness is what a healthy run looks like. Look across the grid. 8 test photos, each captioned with the model's guess and the truth, and all 8 match. Green means the prediction is correct. This sample happens to be 8 for 8. Overall, the model is right about 88% of the time, so a bigger grid would probably show a few reds. Seeing the real images is the sanity check the accuracy number alone cannot give you. The final connector, and the pipeline is now complete. All 6 blocks drawn and wired together. The last block, write the state dict to disk with torch save. The dict of tensors, not the pickled object from the save lesson. One line, torch save of model.state dict in a path Fashion-MLP, PT. That writes 798 KB to disk, and the reload check confirms it. The maximum difference after loading is exactly 0. The weights are recovered. A fresh model plus load state dict gets back the exact weights. ready to classify more images later, as long as they are prepared the same way. That closes the loop from the save lesson and closes the playlist. Let's bring it together. The whole program is one pipeline: data, DataLoader, model, loss, optimizer, save. Every piece a lesson you already know. A plain MLP on Fashion-MNIST, trained with atom and cross-entropy for 5 epochs, reaches 0.878 test accuracy. No convolutions needed. Watch validation track training. The small gap between them is a good sign. It's generalizing, not just memorizing the training set. Save the state dict, and the trained model outlives the run. 798 KB that classifies clothing. One last check. You run it once and see 99.9% validation accuracy after a single epoch. Time to celebrate. No, that is a red flag, not a triumph. A plain MLP on Fashion-MNIST lands around 88%, and this run got 0.878 on the test set. A 99.9% validation score after one epoch almost always means one of 3 things. Your validation set is not truly held out, so it overlaps or leaks from the training data. Or your accuracy metric is broken, comparing labels to themselves or dividing by the wrong count. Or you measured on data the model trained on. When a number looks too good, suspect the setup before you believe it. Trust the honest 88%. You built, trained, measured, and saved a real classifier end to end. That is a complete project, and it is a real milestone. The MLP flattened each image and threw away its shape. Next playlist, we stop doing that. Playlist 2, Computer Vision with PyTorch, brings in convolutions. Layers that read an image as a picture instead of a flat vector and push far past what a plain MLP can do. Congratulations on finishing the basics. See you there.